So hello everyone. My name is Cameron Moye. I'm a second-year graduate student working with Brad Jolliffe at Washington University in St. Louis. Um, and I'll be presenting some results we have from a mixing model that we've been working on for estimating the amount of SPA material that we can find at the different Artemis 3 candidate landing regions. Next slide, please. So essentially, studying the any SPA basin samples was outlined as a top priority goal in a variety of different guiding documents like the past two decadal surveys and the Artemis 3 Science Definition Team Report. And collecting and analyzing SPA samples is important for a variety of reasons. Um, Mainly chronology to help constrain the period of late heavy bombardment on the moon, as well as models for early migration of giant planets, as well as uh, these samples may provide our first direct samples of the moon's mantle because of the size of the impact, and new samples of the lower crust that we may not have gotten from before. Um, and Any samples will also help us test models for giant basin formation, which is of course applicable to all other planetary bodies. Next slide, please. So, as you heard in the previous talk, there's likely SPA material within each of the candidate landing regions. What we set out to do was figure out how much of that can be found there. So, you know, the South Circumpolar region in the Artemis 3 exploration zone lies pretty much on the rim of the South Pole Aitken Basin. So material was probably deposited there, but over billions of years of subsequent impacts, it's been mixed and churned and diluted and whatnot. So what we're looking at is iron abundance and thorium abundance from the lunar prospector gamma ray spectrometer. You see the iron abundance in the image on the right here. And you see as you go from the South Pole Aitken Basin to the Feldspathic Highlands across the South Pole, there's a fairly linear decrease in both FeO and thorium abundance. So we can use the average abundances for the South Pole Aitken Basin and averages abundances for the Feldspathic Highlands as sort of end members for a two-component mass balance to figure out the estimate of the percentage of SPA material present at each of the candidate landing regions, or CLRs as I'll refer to them. Next slide, please. So to do this, initially we used the Lunar Quick Map by drawing a series of traces that go from the SPA in an area of relatively high FeO and thorium abundance across the South Pole through each of the candidate landing regions to the southern Feldspathic Highlands on the near side. As you can see, here's two examples of these traces, one in iron on the top and thorium on the bottom. This is the trace that goes through the connecting ridge extension in Malapert Massif regions. Next slide, please. So, sorry for the large table, but some results that we got for landing regions on the near side of the South Pole. We're estimated about 30% SPA material on average is present at those sites. And landing regions on the far side, closer to the South Pole Aitken Basin, were about 45% SPA material on average. Essentially, to get those numbers, we took the independent FeO and thorium percentages and then combined them using a sum of squares optimization to get our final SPA material fraction. The highest one was the Daguerreauloge Kosher Massif. It had a SPA material percentage of about 62%. Makes sense. It is the one that is closest to the South Pole Aitken Basin. We had some higher than expected SPA material estimated at the Nobile Rim 1 and Leibniz Beta Plateau sites. These are a bit further, these are fairly far away, but they were on average higher than we expected them to be, which is something that we're looking into. But overall, I think we can say that there's a non-trivial amount of SPA material likely to be found in each landing region. These are, of course, just estimates, but yeah, based on the high amounts that we're seeing in each one, we uh, can fairly confidently say that there's probably a decent amount at each of these sites. Next slide, please. So something that we were also looking at was potentially incorporating the Kaguya spectral profiler data. You saw the plagioclase data in the previous presentation from Lamellan et al. 2022. They also have FEO abundances. We see a similar decreasing trend that we see in the Lunar Prospector data. So there was a potential to incorporate this data into the mixing model. However, there is a bit more variation in this data. So the errors on the average abundances for each region were fairly high. We're not entirely sure if we can see the same kinds of trends that we saw before. However, the higher spatial resolution of this data is better for local analysis of the Artemis 3 candidate landing regions. Instead of having 1 or 2 pixels per landing region, you have a whole bunch of them. So that is something that we're looking into as well. Next slide, please. So we saw some similar other mineral trends, so decreasing trend in pyroxene, mainly low calcium pyroxene, because it's much more abundant in the south polar region than high calcium pyroxene, and an increase in plagioclase. There is a much higher variance in these data sets, though, so as you can see, the spread in the two plots here, plagioclase on the left, pyroxene on the right, means our error bars on our averages are fairly large, and it's kind of hard to. There is a rough trend there, but it's maybe not as confidence-inspiring as the Lunar Prospector data. Next slide, please. So here are the average abundance for plagioclase, low calcium pyroxene, and FEO from the spectral profiler data at each of the candidate landing regions. And in the lower right, you have the averages for the Lunar Prospector FEO for each of the candidate landing regions. As you go farther out from SPA, in the spectral profiler plots, you'll also see a few leading points. These are just 200, 300, and 400 kilometers from SPA to show a bit of a trend. Interestingly, we see a similar trend near the pole that you saw in the previous presentation, where things like plagioclase are heightened. Of course, as you can see, the error on these is fairly large. Each of the error bars is just one standard deviation of the average of the data for that region. There are error bars on the Lunar Prospector data as well, but they're just very, very small because there is such a low variance in that. But yeah, this was something else we found interesting and haven't had too much of an opportunity to look into just yet. Yeah, next slide, please. Here is sort of like a little case study of the Malapert Massif candidate landing region. So we get an average FEO of about 6 weight % for from the Lunar Prospector data for this region, and an average of about 7.4 weight% from the Kaguya spectral profiler data. This comes down to, or equates to about 31% SPA material from the Lunar Prospector iron and thorium abundances. And then, so even in one of the landing regions that's farthest away from the SPA, we do see still some relatively decent proportions of SPA material in this candidate landing region. Next slide, please.
So we're at time. Oh, looks like you're just wrapping up.
That's what I've got. So thank you all
Feel free to wrap up.
for listening. Yeah. So, and special thanks to the LROC team for their support and their continued support of Lunar QuickMap, NASA for their support of the Artemis program, and you all for listening and the opportunity to speak today. So thank you.
All right. Thanks, Cameron.